Good morning, everyone. My name is Mark Felicelli, National Product Manager with Graybar Electric, and I would like to welcome you to Graybar's G2 Talk presentation on VFD drive cable, critical or overkill. This talk is part of a webinar series we offer each month for our customers. We have a great discussion lined up for you today, but before we get started, I would like to cover a few housekeeping items. First of all, if you were one of the first 50 people who joined in on this presentation, you will receive a coupon for a free cup of coffee courtesy of Graybar as a thank you for your time today. Also, at the bottom of your screen, you'll see a Q&A box. Feel free to submit questions throughout the presentation. We'll address as many questions as time permits at the end of the presentation. Lastly, our G2 talks are all archived on the graybar.com website. You'll be able to view this presentation again or recommend it to others. We're happy to team up today with General Cable Corporation. As a full-service distributor, Graybar works alongside General Cable Corporation to provide the solutions from network deployment, network performance management, and troubleshooting, as well as security and performance monitoring. You can visit graybar.com to learn more about these solutions. At this time, I'm happy to introduce today's speaker. Today we have with us Sujata Sullivan, Director of Sales Industrial Automation for General Cable Corporation. Suji is responsible for increasing share in the industrial automation market. She brings to this role over 20 years of industry experience in various positions, including product development, product management, manufacturing technology, and sales. Suji holds a Bachelor of Science in Mechanical Engineering from the University of Texas at Austin. So without further delay, I will turn things over to Suji to begin today's presentation. Take it away, Suji.
I want to first of all thank you, Mark, and thank you, Graybar, for having me speak today. And thank you, audience, for your time. I'm Suji Sullivan, and I am happy to speak about a topic that I find very important in today's industrial automation space, variable frequency drives. Then I'm also going to talk about the cable that's involved in the variable frequency drives. Is it critical or overkill? Now, variable frequency drives are getting more and more interesting in the industrial automation space, and they're a powerful asset because they're helping manufacturers improve efficiency. And so more and more manufacturers are upgrading to VFDs. These are powerful yet necessary evil because they introduce some complications to the system that need to be figured out and designed for. And we are seeing more and more applications in using VFDs for many different industries: water treatment plants, metal production, chemical industry, power plants, paper and printing, oil and gas, mining, food, clean rooms, hospitals, theme parks even. The main reason is to control flow, to coordinate speeds, to vary the speed, startup and torque, and to conserve energy. So anywhere where you can actually manipulate the drive, the motor speed, you need to use a VFD. So why are VFDs being used? Well, manufacturers are realizing greater efficiency and faster return on investment and profitability. They're seeing greater system reliability, reduced downtime, and reduced equipment setup time. And the biggest factor is they're really seeing a savings in energy. So if you run a motor at 50% of its time, if you don't have to run it 100%, you just use it 50% of its time, you will actually reduce your energy use by 90%. 90%. And that can also lower your maintenance, and you can have a smoother operation, or what's called a soft start, using a VFD drive. Another reason is, along with the speed control, you have flow control, you have pressure control, temperature control, you can control the torque, the tension, you can monitor the quality, you can actually control the acceleration and deceleration and ramping up speeds. you have basically better control of your whole system using VFD drive. These applications are multiple. You see them used for pumps, hot water pumps, condensed pumps, booster pumps, conveyors, fans, cooling towers, circulation fans, exhaust fans. I was just at a game recently after the game, this was the Caps game, I went to my car in this crazy, parking garage, and you have a lot of cars trying to leave at the same time, emitting the CO into the air. And the whole time I'm thinking, my God, this is not good. So that now you're seeing more circulation fans being used in parking garages, and they can be controlled with VFD drives, so they're not used constantly, but only when they're needed the most. So that's another really good application. To understand how a VFD system works and what parameters need to be considered, let's look at the system. You basically have a variable frequency drive, and you have it control a motor. So between the variable frequency drive and the motor is a cable. That cable is what people don't seem to think about. It is the least considered part of the system, but actually can be a huge component in terms of reliability and the way the system actually works, if some thought is put into it ahead of time. If you look at a system, sorry, just a moment. So what we see in this system is critical concerns from newer technologies. You have problems with premature motor failure, premature cable failure, malfunction of other equipment, and complete shutdown possibilities. The cause is the high frequency components that the inverter from a VFD can actually provide. This causes electromagnetic interference, common mode current, and reflected waves. We'll go through this. So in a real world system, you would have the frequency drive, a variable frequency drive connected to the motor with a longer length of cable than we normally would have expected just because of the way the system is supposed to be. Then you have several of them. You don't just have one. And then along with that, you have different control systems. You have electrical systems, communication systems, and people. So there's a lot of chaos happening in this manufacturing environment. So how do we take care of that chaos? You have to manage it and have a good design. So to do that, we have to understand the system parameters and the effect that the drive has on the motor, and then that means the effect it has on the cable itself that connects the two. This is kind of a mock way to show the effect. You have the cable length as part of this equation, the type of cable is part of this equation, the bonding, the motor type, the rise time that is created by the variable frequency drive, and the termination. All of these can cause issues. So altogether, you can have a formula that's creating evil and increasing cost if you don't take things into account to take care of these issues. So the reason for this, to understand the system parameters, we have to kind of go back to how we've gotten to where we are and what VFD systems actually have in them today. In the past, VFD systems had transistors that they use, semiconductors they used to use called BJT or bipolar junction transistors. And now the newer ones are called IGBT or insulated gate bipolar transistor semiconductors. These aren't very new. I mean, these have been out for over 10 years. But they're getting, because of the more and more sophisticated designs of these coming into the VFD drives, we are seeing more and more havoc that they can cause in the system if it's not well regulated. So these more sophisticated semiconductors actually provide lower switching costs loss. It actually brings down the drive packaging costs. It creates faster transition rise times, and in that process, it also provides a higher frequency or pulse wave modulation, which becomes the issue that we have to take care of. What is high frequency or pulse wave modulation? In a 60 hertz that's provided to, in a normal system, you have 60 hertz waveform, which is a sinusoidal waveform. With the pulse wave modulation that the IGBT semiconductors or the actual drive creates, it actually takes pulses and digitizes them, pulses of voltage, and digitizes them and creates these amplitude pulses in a sequence where it kind of makes a pseudo waveform. Even though it's a square type of form, it creates a voltage waveform that becomes kind of like an AC waveform. But in doing so, it is actually a digitized process, and this causes the problems. Herein is the evil. And then another evil is, although it's a good quality for the manufacturing process, you have a fall in rise times. Over the years, with the improved efficiency of the IGBT transistors, you see that we have increased or completely made a very short time for the voltage spike to go up. So you see that fall in rise time is detrimental to the system, and I'll explain why later, but it's an excellent feature that the new IGBT semiconductors provide. So the critical concerns, again, from this newer technology, as I had explained earlier, is you do see premature motor failures, premature cable failures, and possible complete shutdown. The high-frequency components of the inverter output create the electromagnetic interference, common mode current, and the reflected wave. These are the evil that they create, and this is what we have to take care of. So let's talk about the electromagnetic interference. That consists of electromagnetic radiation and electromagnetic induction. So these two we will talk about in a little more clarity. Electromagnetic radiation is basically creating a radiated loop antenna that can be created from your system if it's not well grounded. So you get the radiated noise negatively affects the instrumentation controls, the radio devices, all the alarms, and the severity is really related to the distance you have from the cable and the equipment. Sometimes you don't have a lot of space there. And the design of the equipment is important. And of course, the high frequency information at the inverter output waveform is very critical to this. Also the terminations to make sure you have a good grounded system on both ends. And the type of cable. The shielding between the cable and the equipment. All of these things contribute. So is the cable important here? Electromagnetic radiation is very important to account for. Why? Because it can kill equipment, it can kill drives, and it can kill people. This is very important. So an effective cable is critical. An effective cable can have an overall shield that greatly reduces that radiated EMI. The shield and ground wires need to be terminated as directed by the manufacturer of the drive, and there needs to be a 360-degree termination of the cable shield to make sure you have a good, effective cable system. The other thing I wanted to talk about is electromagnetic induction and common mode current, another evil in this process. So electromagnetic induction is produced when a voltage, it produces a voltage across a conductor when it's exposed to a varying magnetic field. Well, we see this happen with VFD drives because you're inducing a magnetic field when you're rectifying the AC to a DC voltage and then inverting the voltage back to AC through the rapid switching that the IGBT semiconductors provide. Common mode current is the total net flow of current in the cable. Most of the time, you want this total net flow to be 0. And if you look here, it's the current that's in the conductors, in the ground, and in the shield. They all should equal 0 for the least problematic situation. However, that is not the case with high frequency modulation. What we see, the common issues, and you can see this, is with the motor bearings. If you see premature motor bearing failure, it's very likely that that's from the cable not being adequate for your system and the common mode current issues with that. You can see interference from PLCs, PLC communication networks, sensors, encoders, AM radio interference, all sorts of possibilities. You also see shock hazards because there are voltage potentials that are created along the inverter frame and motor frame that are really high, sometimes close to 100 volts higher. Why does this happen? Here we go again with that high frequency wave, pulse wave modulation waveform. You see, with 60 hertz systems, you have the phases all 120 degrees apart. You have a three-phase voltage waveform. And in this, you see, because of the phases are 120 degrees apart, they all cancel each other out. And that's a 60 hertz system. With the common mode source, like you have with the pulse wave modulation from a VFD drive and the high frequency, this is not what you see. What you see is a digitized square wave that we're trying to create an AC, a pseudo-AC form from. And in the process of doing this with the high frequency and rapid rise times, what we're seeing is there's actually the peak voltage actually has voltage on top of voltage that happens. It's a phenomena that creates extra voltage that is not seen in normal 60 hertz waveforms. So this high frequency can cause trouble because you're having more standing waves over time at a higher voltage than needed, or than what you account for. So the common mode current will cause that voltage potential difference between that ground and the motor frame, and that is from the impedance mismatch between the cable and the drive. And when you have the drive cable attached to the drive and you're seeing this, creating this high frequency pulse wave modulation waveform go through there, if the cable doesn't account for that, it will definitely cause issues. And there's a leakage of current that the voltage causes from the motor frame back to the inverter frame, and it all gets into the system and causes harmonics that are really unnecessary and unwanted. This is current that does not do anything but cause problems. So what happens is you want the cable to be able to take the current, the cable to take the current and bring it back through the ground, and so it takes care of that excessive current that's in the system. Well, what happens is a lot of times when you don't have a proper system, the current finds a way to leak any which way it wants to in the system, and this is what happens. So this would be a common mode current that goes through from the drive to the motor. Where is it going? There's several paths that this can take, and not good ones. You don't want it to go through the ground conductor. For a high frequency system, that is not a good thing. Now why? It's a really good path. A cable ground conductor is a really good path for 60 hertz power. It is not a good path for high frequency components because as the frequency goes up in this formula for resistance or impedance of the system, the wire, the resistance goes up. When the resistance goes up, well, guess what? The current doesn't want to go in that path. It wants to take the path of least resistance. It's going to find an alternate path. So here we've got other possibilities that the current will want to take. You can see many different methods of where the current's going to go. You just don't know depending on the potential. See, when you have a potential difference at the motor frame versus the inverter drive frame, look at how the current can flow. It goes back through and goes back into the inverter. So wherever it goes, the current's going to cause trouble. That common mode current will cause trouble. It can even go through the motor frame and through the equipment, through the shaft, through the mine equipment, create another voltage potential difference, and then find a way through and cause damage to the mine equipment as well. So either it causes damage in the motor, causes damage in the equipment, or causes damage somewhere else along the way. The best case situation with a common mode current is to have it go back through the shield of the cable. If you can have it go back through the shield or armor from the motor frame to the inverter through the cable shield, you have to have a very well-designed cable for it to do that. That's the best case. You don't want to use a conduit as the shield, however. So to repeat, this is the current may flow through the motor ground cable, from the motor terminal box to the inverter ground. The current may go through the motor frame to a grounded motor base plate. It can travel through any and all conducting paths to the ground grid and back to the transformer ground, and finally back to the inverter ground. Another possible path is for it to take an alternate path of equipment connected to the motor through the shaft and through the connected equipment, causing trouble along the way. And then lastly, current can flow from the motor cable shield, armor, or conduit. You want to make sure it goes through the cable shield. So you want to make sure the cable shield is actually creating the least amount of resistance for the common mode current to follow. So the design of the cable becomes critical. An overall shield provides a large surface area with low impedance at high frequency. And that's key because you are working with high frequency when you're working with VFD. So you need a large surface area. That's what a lot of cables do not afford. If you don't provide that, you're not going to get what you want out of this. So to create that lower impedance path and to reduce the voltage potential at the motor, you need to have a very good large surface area shield. And a braided shield can provide that because not all shields are created equal. Terminations and the way that both ends are terminated with 360-degree contact of the shield is very important. You want to make sure the cable itself is not promoting the common mode current. So in many ways, that shield is very effective to your whole system. Another thing to consider, because cable design is so important in this, is the difference in design makes a key difference in the way the cables behave. So if you look at this on the left here, you see 3 conductors on the ground. It's one single ground. let's look at the way that the voltage, you have the three different phases, the way they behave. You see the voltage, the green shows the voltage, actually has a slight waveform to it. So that shows that there is a voltage potential created by the cable itself. Now if you look at the right, you have three grounds all put into the cable in a symmetrical fashion. And what happens here is because these are evenly spaced, you will see that the green here shows the cable, the voltage created by the cable is minimal because they all cancel each other out. Now this happens because if you look on the left, look at the arrow, you're seeing the distance to the ground is different from each conductor. It's important. So that's where you see the differential. If you look at the distance to each ground from each conductor on the right-hand side, they're even, so they cancel each other out. Another phenomena that we need to talk about is reflected waves. So reflected waves is another aspect of the high frequency modulation and the rapid rapid rise times that is causing issues with the VFD system. Peak voltage spikes are caused by the impedance mismatch I was talking about earlier, which is not an issue for 60 hertz traditional power systems. But when you actually have the high frequency drives, you are creating pulses of voltage that's going through, and at the same time you're getting a reflected wave come back to that comes back. And I'm going to show you how this works. The voltage pulses go through, and if you see, I think you can see it move here, then you get the reflected wave comes back. When the reflected wave comes back and actually gets higher and is not in sync with the others where they get canceled out, you see that you can actually have double the peak motor voltage. That requires special design consideration to eliminate. Another evil in the system. So this reflected wave phenomena actually creates higher voltage stress than in traditional systems. This can cause damage to the cable insulation. These higher peak voltages definitely create problems in insulation, and you see instantaneous high voltage spikes, which we call higher VVDT. So it's a change in voltage over change in time. Insulation compound of the material that the cable is made of, the insulation, becomes very critical. You want to make sure that it does not get damaged by this kind of phenomenon. So thermoset insulations have a proven track record for alleviating that. Thermoplastics, sorry, there's an incorrect information here. PVC insulations actually cause issues. I'll go over that in a minute. So if you look at reflected waves, let's first look at a case study of 480 volt drive system using a 650 volt DC bus voltage, and you use 100 feet of cable between the inverter and the motor. So keep that cable distance the same. Using an older drive type with the BJT technology, rise time is 1 microsecond, and the peak voltage is 780 volts. With the newer technology, the rise time is 100 nanoseconds, and the peak voltage is 1300 volts. Cables can see twice the drive time. Just a moment. I just lost my presentation. One moment here, sorry. Okay. Sorry, I clicked on something. I'm getting trigger happy here. So when cables can see 3 times the operating voltage sometimes as well, you have to make take that into account. So faster rise times mean more standing wave issues. And the distance between the drive and the motor needs to be really, really short using the better technology. So manufacturers that have old technology drives are not going to have the same issues that you see today. And so people are used to using the old technology, and they use the old type of cables for that technology to connect the drives to the motors. Well, they don't work for today mainly because of this. So as you can see, you need to, with the IGBTs, because of the design, you're going to have a really short distance between the drive and the motor, unless you take into account the proper system requirements. That means a good cable. Again, there's the evil. We've got to keep that in mind. So the cable design is critical. We need to look at the insulation. PVC insulation is what is used for THHN cables. THHN cables were predominantly used for the older style drives. And they were fine, completely fine using those style drives because of the older technology. The newer technology does not allow you to use them. So PVC, why is it good? Well, it's relatively inexpensive. It's flame retardant. It's easy to strip, flexible. But the negative aspects is it's hygroscopic. And what that means is that it can actually absorb moisture from the air. Even if you don't have water near you, it's going to take it from the air and change its actual capacitance of the cable and drop its dielectric. And that changes the properties, electrical properties of the cable itself. Another phenomenon is that it can cold flow. So what does that mean? If you have some type of pressure that you have on the cable, over time, that insulation will be displaced by that pressure and create a lessening, or the thickness will actually go down. When that happens, you're going to see a change in the way that it behaves and the impedance change in the cable. So how about 600 volt cable? Let's look again at a 480 volt standard power system. Can we use it on a 480 volt VFD system? It's fine on the 480 volt standard system because the RMS voltage on a standard system is 600 volts. And the peak voltage from a standard system is 678 volts. But if you and it's rated to 850 peak voltage for that system. If you look at a 400 volt system for VFD drives, you're going to get 1300 peak voltage. That is not going to work with when you actually have a 600 volt cable because it's rated for 850 volt peak. Also, the high frequency pulse wave modulation is going to add that stress that we were talking about with the high DVDTs. So this is a slide that actually shows you, I've taken a page out of Schneider's guidebook on how long you can have your motor cable. So let's look at this. Let's say we have a 20 HP motor, and then we want to actually have our equipment. We need the drive away from the motor by like 500 feet. Let's take that as a possibility. Well, in order to do that, if you look at all the possibilities there for this, you need to have some type of motor protection filter in order to get that distance. So if you even look at 20 feet or 100 feet, it says for a shielded system, you don't need that. You don't need to consider anything. But if anything more, then you're going to need either a 3% load reactor. You're going to need something to account for it. That is good, and that will help with the reflected wave phenomenon. What it does not help, however, with is the common mode current. that sneaky, leaky current is a havoc that cannot be taken care of. So here are the risks and costs, in summary, of common mode current. Causing motor failure because it flows through the motor bearings and causes the fluting and premature motor failure. We have 100 volts that can be measured between the inverter and the motor that can cause a shock hazard. Don't want to see that. And then we also have the other risk of lethal currents that leak through, and you basically go in an unshielded, locked out inverter to motor cable. That can actually cause a life or death situation. If you look at all this, can you afford this risk? Is the VFD cable too costly now? So that is what we have to think about, that evil that is created from the VFD drive. What can we do about that? We have to look at investing in a good motor cable. So in summary, the VFD cable is critical to the VFD system. VFD cables, the safeguarding features are an overall shield to reduce electromagnetic interference and radiation, a controlled path for the common mode current to flow, symmetrically designed conductors, that way you would minimize induced currents, and robust insulation. That way you increase the resistance to voltage peaks and high DVTs that stress the insulation will not cause problems with the cable itself and wear out the cable in the process. So that, to summarize, the VFD cable design is critical. So this is a way we can conquer that evil and really find a good solution for using this amazing new technology of using VFD drives for our processes and increasing our efficiencies. So General Cable provides many different types of VFD cables, and we have many types of grounds. Depending on the type of application you have several different possibilities. Some of the best, however, would be our mining cables. If you look, the mining cables, they go from 2 to 15 kV, so we have a huge range, and they also have the best type of material for it in insulation, which is an EPR, which is better than a cross-linked polyethylene material that's used on a lot of very good VFD cables. So altogether, you get this material insulation better, you get a really good shield with the aluminum tape and a copper braid, and you have symmetrical grounds, and you have a whole list of voltage, a whole range of voltage possibilities, 2 kV to 15 kV range. So in the mining cable, the critical 3 are taken care of. You have overall shield, you have a symmetrical design conductors, and you even have the ground check, which is symmetrical, and you have a very good, robust thermoset insulation in the EPR. Other features is it's flexible because it's stranded, finely stranded conductors. It's very durable, and we have conductor range sizes from 6 to 500 kcmel, and it's mine MSHA rated, certified. If you look at the designs again, we have many different types of VFDs. The mining ones actually have what you see is a symmetrical grounds, and in the center you have the ground check. So there's no, it really reduces the balance or imbalance possibilities and makes the cable be an excellent feature in the whole system. With that, I'd like to conclude and thank you for your time and turn it back over to Mark. Really appreciate your time today. Mark?
Thank you, Suji. That was an excellent presentation. At this time, we would like to address some questions that have been submitted. As a reminder, you can submit a question using the Q&A box at the bottom of your screen. If we don't get to your question, a Graybar representative will follow up with you after the presentation. If you would like material specifics, please type datasheet into the Q&A box. A Graybar representative will reach out to you for material specifics to make sure we get you the right sheet. So the first question we have for you, Suji, the question came in from Bob, says, why is the cable ground not a good path?
So the cable ground is not a good path because with a high frequency that the VFD provides, that pulse wave modulation with a high frequency, as you increase your frequency, the resistance of the cable ground increases. And when that resistance increases, the common mode current finds a different path to ground because it's going to avoid the higher resistance path. So that's why it is not a good conductor for high frequency systems. Does that make sense?
Yeah. Next question, does the motor horsepower of the application have any impact? Is it less of an issue with a half horsepower motor versus a horsepower motor?
So that's a good question. It does make a difference. Of course, the higher horsepower motors are going to create more issues, and you have to design the cable for those the higher horsepower motors. You're going to make sure you have the proper cable for the horsepower. So we can help you with that if you need some assistance on figuring out which type of cable you need for your motor. So that is definitely something you need to consider. Thank you for bringing that up.
Thank you, Suji. How about how much larger is the OD of a VFD cable versus non-VFD cables?
Ooh, that's a good question. VFD cables have a lot going on, so yes, they will take. They tend to be less flexible and larger diameter. Definitely, if you look at them, they look like batons. You know, they're very, very solid, very, and they're there for a purpose. So they can definitely cause. I mean, you have to design that into your system. So that's why I think people tend to go for something that's easier and more flexible to work with and don't think about it. But in the long run, if you design for it and you think ahead, you're going to create a much better system. And with the brownfields, you do need to take some consideration on actually how to incorporate the VFD cable into the system. It's well worth the effort. It's well worth that diameter change.
Okay. Next question, how does VFD cable help with harmonics?
So the VFD cable, well, the main reason it helps is insulation is definitely a big proponent. It actually helps with the insulation and with also the shield. The overall shield, as long as it's well grounded on both sides and you have a 360-degree connection on each end, you're going to be able to keep electromagnetic interference out of the cable, and you can help with those harmonics. So you basically alleviate a lot of those problems with harmonics using this cable from several different factors, and also the symmetry of the design on how you have the cable conductors placed inside the cable and how you have the ground conductors in there as well. If it's symmetrical and balanced, you can help with creating a more balanced system. So, and that will also affect the harmonics.
All righty, I think we got one more here for you, Suji, that we have time for. Why is the conduit not a good ground path?
So The reason you don't want it to go in the conduit because it has the leaky common mode current can have the tendency to go in different ways through that conduit path. If you go through the cable shield, you're going to have a much better way of controlling that path. And if you have that leaking current on the conduit, if you touch it, I mean, that is a hazard. So you definitely don't want to have that happen. You want to make sure the cable ground takes all of the leaking current.
Thank you, Suji. I think we're about out of... I'm sorry, go ahead.
Sorry, I just wanted to say that that's why it's important to make sure you have the right cable, because it needs to be able to take on that common mode current.
Okay, I think we're about out of time at this point, so if we didn't get to your question, a Graybar representative will follow up with you after the presentation. As a reminder, this presentation will be archived on graybar.com website. Again, thank you for your time today, and we hope you will join us again for the upcoming G2 Talks.